And as I said at the beginning of class, the reason I'm going to be talking about this is because for your semester projects, I'm going to expect you to think about at least one of these topics or something vaguely related to them for your projects. Let's go ahead and get started. So what are we going to talk about in this class? Well, we're going to talk about random hashing a little bit, since that's something I care about, probabilistic sketching and streaming algorithms, matrix decompositions, including maybe like non-negative matrix factorizations and probabilistic decompositions, random graph theory, percolation theory. This actually has some really nice connections to material science, which is not something we see as much of in like sort of data science as we used to. Talk a little bit about wavelet bases. So these are another decomposition of signals, sort of like Fourier transforms. Complexity and entropy. So this encompasses an entire variety of different things, like just how information is encoded and how can you like represent objects. We're going to talk a little about nonlinear dimensionality reduction, and then we're going to talk a little bit about computational topology, mostly just persistent homologies, though we might also mention that there are some nonlinear dimensionality reduction techniques that take inspiration from ideas from computational topology. There are also a series of topics that are possibly out of scope, mostly because they're standard machine learning topics. So there are many other courses, such as Professor Papillon's 1510, which I know some of you took. But yeah, so these are topics that many of which these will be covered in other machine learning classes. So I'm not going to cover them unless you guys really want me to. I might briefly mention some, like clustering. That's a very common task. Linear classifiers. So given some number of features, can you separate out a space into two different classes or more than two different classes? Kernel methods, what are transformations you can do of this data to make it easier to separate? Deep learning, which is just a bunch of classifiers chained on top of each other, and graphical models, which are ways of modeling distributions in a nice compact format. We're actually going to start today by talking about all these out of scope topics. So I'm just going to go through a brief overview of all these out of scope topics. You are allowed to do one of these out of scope topics for your class project if you want to. I know several people ask me if they're allowed to do something a little bit more machine learning-y. The answer is yes, though it's not necessarily the most interesting since everyone's doing that. I mean, it's super interesting because everyone's doing it, but it's not necessarily that novel. So let's start by talking about like what machine learning is and why it's stuff that we're not going to focus too much on. So the basic intuition behind machine learning is that there's some underlying probability distribution generating the data we care about. And we want to try to learn the parameters of that underlying probability distribution, maybe with some a priori assumptions. So the general overview is some algorithm builds a mathematical model based on your training data, which it then uses to make predictions or decisions on new data. And we say that the model parameters are learned from the data because those are free variables that we then optimize for in whatever method we use for training. And there are a number of different ways you can do this. In my exposition today, we're going to focus on the supervised classification task, though many other topics are usually considered as within the scope of machine learning, but just because this is easier to explain in the 20-minute Whirlwind overview. So what are the basic aspects of machine learning? Well, you have something called a linear classifier, which is basically if you have a bunch of data points that are scattered around and you have, say, two different labels, say half of them are from mice and the other half are from men, well, maybe you want to use all these different metrics about mice and men and then classify, and then based on some new data point, figure out whether it's a mouse or if it's a man. And the way you formalize this mathematically is given an input vector, you take the dot product of the input vector with some weights vector, and then you apply some functional transform to it. And then the weights should be constructed such that you recapitulate your labels on the training data. And hopefully this means that you'll get the right label on, well, test data as well. So a simple example is you can just create dividing hyperplane. So this is where you're basically just asking, are you on one side or on the other side of some hyperplane in a high dimensional space? And there are obviously different hyperplanes you could choose. And so that would still divide up your training data. And so like which hyperplane you choose is a matter of some taste, and different methods do different things. So for example, some of you may be familiar with the perceptron algorithm, which just finds some hyperplane that goes through the origin. Other methods that also do similar things are things like the support vector machine, which tries to find the maximum margin hyperplane. So somehow you have all these different hyperplanes that all work equally well on your training data, but maybe there are ways of choosing hyperplanes that give you more room for error. So which give you more room so that if your data was noisy, you would still get the right classifications. So this is a matter of a lot of study because this is obviously an important question. Like, how do you classify cats versus dogs? Which is one of the great questions of the internet age. There are other tricks you can use. So instead of just doing dividing hyperplanes, well, your data might not be linearly separable. And if it's not linearly separable, we may want to map the data to another space where it is separable. So for example, if you had some data here and you had another set of data out here, which were around, well, and you want to separate that out, there's no hyperplane you can draw in 2D that will separate the two of them. But what you can do is you can lift this data into a higher dimensional space using some kernel function. And when you do that, if you use the right kernel function, it will actually cause your data to separate. And so, for example, for this particular example, if you lift the data by taking everything up parabolically, then the stuff here in the center will be nicely separated from the stuff out here by a linear separation. And you can sort of see this in this example here. Back before the days of deep learning, this was one of the things that people cared a lot about, was just trying to find the right kernels to allow you to separate your data in a nice way. These days, with deep learning, often we just automatically learn the various transformations that you need to do it, to do things like this. Oh, why is it? Come on. Why is it not working? I'm very confused right now. Well, let's try that again from current. I think somehow typing on here messed it up. Okay. So some of you may have heard of deep learning. It is a super popular topic because it's an incredibly powerful technique for basically what you do is you chain together a bunch of linear classifiers and add the tiny nonlinearity to each of them. Usually this is represented as this, this neural network where each one describes the relationship between any particular variable and which linear transformations you're doing to it. You combine these things together, and this allows us to, whereas in the previous slide for the kernel functions, we had to choose some carefully crafted special nonlinear function to separate our data. It turns out if you just do a bunch of simple nonlinear transformations, such as a ReLU, which is just this super simple nonlinearity. So if you just do, if you do a bunch of them, that can allow you to approximate basically these complicated kernel functions without relatively quickly. And these things are easy for modern computers to compute. Okay, it seems that once I type and draw anything, I become unable to switch slides, which is a little bit of an issue. Ah, there, okay. And the nice thing about these deep neural networks is you can actually learn all of these weights. So using back propagation, which basically just means, which is a fancy word for gradient descent. So you train on some data, you are either correct or incorrect. If you are correct, great. If you're incorrect, well, then you can see the reason that you were incorrect at the previous layer. And you can update all those weights to make things slightly better. And you can see the reason those weights were incorrect. And so you can back propagate by basically using the chain rule. So you can back propagate and you can compute by computing the gradient of each layer from the back to the front. And this allows you to update your weights. And if you do this 10 million times, it turns out that the weights for your network become good at approximating some arbitrary function, some arbitrary classification function you care about. Okay, so that's deep learning in a nutshell. Other tasks that people have traditionally worked a lot on is things like clustering. So that's just basically grouping together data points into meaningful groups. Now, in some sense, classifying is very similar. So the supervised classification task is very similar, where you know your two meaningful groups and you're trying to find a separation between them. But what if you don't know the two meaningful groups to begin with? Well, in that case, you might just want to partition into two groups that are similar in some way. So there are two major versions of this. Well, at least two major versions. One is you have some high dimensional space, and then you might want to partition these cluster these data into each of these three different colored groups using something like k-means, or there are other techniques. Alternately, you can also do it on the graph. So if you have a graph, maybe you want to cluster together all the nearby graphs into coherent modules that somehow behave coherently under some dynamical system. So like these are two of the major issues with two of the major problems in clustering, and this has been worked on for decades, even prior to the current machine learning revolution, because in fact, Some of these things go back to social science in the 1970s, I want to say, where people were just trying to understand the social dynamics of group formation. And of course, you have slight variations on like hard or soft, depending on whether you can be a member of multiple groups or if you have to be a member of only one group. One of the most popular methods, which you may have seen, is k-means. So given a set of observations, you want to find a partition that minimizes squared distances to the cluster centers. And there are a number of ways of doing this. One is this naive k-means algorithm. You just randomly start with different centers, and you iterate. So you assign all your clusters based on your initial based on how close they are to your initial centers, and then you update your centers after you've assigned those clusters as to minimize the distance from the center within each of your clusters. And you do this over and over again, and this turns out to converge if you're using Euclidean distance. It doesn't always work if you're working with other distances, and that is, of course, a topic that people still care about. For graph clustering, often what you do is on a graph, you repeatedly cut the graph in half, or I mean, cut the graph in such a way that you minimize the cut weights. So like if you think about the edges as the things you're cutting in half, well, maybe you do this repeatedly, and each time you're trying to minimize some function of the cut weight. Alternatively, you can also go the other way and link together nodes based on how strongly connected they are based on the graph edges. And there are a bunch of different scoring functions people have come up with for these kinds of things, ranging from things like Gervin-Newman modularity, which was a super popular one and still is to some degree, which is just the fraction of edges from the cluster minus the expected fraction if the edges were distributed at random. This is actually quite related to some concepts in physics. So it turns out that the graph clustering problem is mathematically equivalent to measuring the Hamiltonian of spin glasses. Getting the energy of a system where you want adjacent nodes to have the same spin in a physical system. So there are some nice mathematical connections there. Another thing is you can also have the cluster scoring function independent of the number of clusters. So this can be paired with a hierarchical clustering to discover the number of clusters instead of having to input them like you do with k-means. You guys should stop me at any point if you have any questions about any one of these topics. I'm going to be going pretty quickly since I just want you to get a taste of what's out there, even if we're not going to have time to cover these in depth. Let's see, what time is it? What time is it? 3:50. Okay, I have 10 more minutes. So there are other things that also form part of sort of traditional, what I classify as machine learning. One of these is something called a Gaussian mixture model. We talked about these briefly when we talked about separating out mice and men as different Gaussians, right? And so the basic idea is if we assume that our data set is generated by a combination of different Gaussians under some parameters, well, can you separate that out? So if you know that your data set is generated by some number of Gaussians, can you figure out what points in your data set were generated by which Gaussian when you get a new data point? And so can you estimate all these parameters based on drawing this sample from it? So and the answer is often yes. And there are a number of different techniques to do this. Often these are actually, many of the simpler ones are based off of the SVD, which we did not cover, but we might go back to later after you guys have covered it in 1850. So there are a number of different ways of fitting these parameters. I'm just going to briefly mention the expectation maximization algorithm because that's a super commonly used one, which you will see in the literature if you pursue this sort of and go in this direction, which is basically you start with random values again, and then you compute the probability of each possible value given your epsilon. And then you use these just computed values of Z, which is these latent variables, these other variables you don't know, and you estimate your parameters again. So you just keep on going back and forth, and you iterate until you converge, which is a very common strategy whenever you're working with these kinds of inference type problems, or we were working with these kinds of machine learning models. You iterate until you get something close to convergence. We saw this actually a little bit when we talked about Gibbs sampling, where you just sort of iterate over and over again until you get something close to convergence, often using one variable at a time, or one set of variables at a time instead of the entire set. Okay, so what are hidden Markov models? So hidden Markov models are a way of modeling a system where you assume that you have some number of unknown parameters, sort of like when you had a Gaussian, except instead of assuming that you just have these Gaussian parameters that are generating some mixture of terms, you assume that you have a Markov chain where you don't know the where you don't know the weights, where you don't know the probabilities of switching from one state to another, but you can observe certain states. And so from those observable states, can you figure out parameters for your hidden states that allow you to predict the classification of points that come in, or like the behavior of the system? And these things can be learned through a variation of the EM algorithm as well. So basically, what you're doing is you have some amount of you have some parameters of a model. You compute the probability of a particular. You can compute the probability of a particular output sequence, and you can also figure out the distribution of hidden states of the last latent variable at the end of the sequence. So basically, this is just some other you have some black box. You don't know what variables are in there, but you know that there's some sort of structural connection between the different variables that you care that are hidden in there. And then you try to infer from your data what those weights ought to be in order to predict the behavior of the system. Another technique is these things called graphical models. Graphical in the sense of graph theory. So not graphical in the sense of like drawing a picture, but graphical in the sense of graphs. And this is, of course, this is a way of representing probability distributions. So, of course, you can write down like some complicated PDF of a probability distribution, but that's sometimes really quite complicated. Often it turns out that the probabilities of a set of variables are dependent on each other, and you want to somehow encode all those dependencies. So maybe if you're talking about the variables that you might measure about a human being, maybe my height is correlated with my weight in some way, or maybe my height causes some change to my weight in terms of observables. And so for that reason, you might want to encode all these relationships between the different variables you're measuring about me into some sort of compact representation, in this case, a graph. There are a couple different ways of doing this. One is to have a directed acyclic graph, where basically you're saying, well, these variables help determine these other variables in this sort of directed way. You can also have an undirected graph, which we would call Markov random field, where the variables are correlated with each other, but there's no like directionality between the way you do things. So with the sort of directed networks, you might have a Bayesian or a belief net. So basically what these do is each variable has arrows pointing out of it to denote which other variables it affects effectively. So a variable is dependent on the variables above it in this directed acyclic graph. You're only able to observe a very specific number of these variables, which we call evidence, but from these you're able to learn things about the probability distribution as a whole, and then you can predict things in a similar way to like with the hidden Markov models. With a Markov random field, each variable is conditionally independent of all other variables given its neighbors. So you're basically saying, if I know my neighbors, then I don't need to know anything else to know my probability distribution. And so you can also encapsulate certain types of probability distributions using these kinds of Markov random fields. And one common example of this goes back to physics, which is the Ising model of spin glasses. So this is, again, related to the clustering problem of community detection. It turns out that, well, this is quite related because if you know the spin of all the particles that affect you. So if you assume that the spin interaction is a local interaction as opposed to a global one, which under some models it is, well, then you only need to know your neighbors to know whether or not your energy is high or low. Another example might be image reconstruction, where you want pixels to be locally consistent, but you don't actually care about like this global consistency. You don't care as much about global consistency. Okay, how am I doing on time? 3:56. Okay, so I think like I'm probably actually going to end off there. And in tomorrow's lecture, it's going to be a sort of whirlwind tour. I'm going to talk about the topics that we are going to cover in this class. So those are all topics that we're probably not going to cover in this class. If you think they're cool, go take a machine learning class. They are really cool, and you should do it. But in this class, we're going to instead be talking about this other list of topics, which are, I think covered a little bit less often than like the standard machine learning methods, and which I think have some really cool mathematics that's often associated. So that will be what we're doing tomorrow, and then hopefully by the end of all this, you'll have some sense of which types of topics you care about. Are we going to do chapter 6 and 7 of the textbook? What are chapter 6 and 7 of the textbook? Let's see, what are chapter 6 and 7? Yes, we are going to do chapter 6. We are not going to do chapter 7. So we're going to do the streaming and sketching and sampling. So that's the second of the topics, actually. We're going to be doing that pretty soon. We are probably not going to do the clustering methods because that's a fairly standard topic in the like machine learning classes. So if you want to go ahead and read ahead, or like there are other courses that will cover that material. If enough people want me to cover clustering, like I'm happy to do it, but like that wasn't on my plan for this course. Okay, so having said that, this seems like a natural stopping point. And then we'll continue with my next 30 or 40 slides on tomorrow, which will give you just a really fast overview of like the sort of flavor of each of these topics. Like you won't learn any math from this. You just learn, oh, exists this topic. This is the kind of math you might use. I won't be proving anything tomorrow either. And then we'll be back to our regularly scheduled programming on Wednesday when we go back to like actually proving all the theorems we talk about and really going in depth. But yeah, so you should today and tomorrow you should really be thinking about which of these problems you care about. And what I'll try to come up with some project proposal ideas. But yeah, there's a lot of cool stuff out there. Think about what you care about. And with that, I will end class for today, and I will see you all tomorrow. Bye, everyone.